Thank you, Matthew. Hello, everybody. Good afternoon. So, this work is part of a no proposal of the CPO and the interplay between sea level and Atlantic regional overturning circulation. The PI is Dennis Volkov, and I have to thank some of my colleagues here for the discussions and the help for some analysis. So let's start. So first, I want to define what marine heat waves are. So marine heat waves are prolonged periods of anomalous ocean warmth in a particular region. So we have regions, we have discrete means in time that a warm anomaly happens during a few days. And this, we define this as marine heat waves. And the opposite would be the cold spells. So we have warm anomalies and cold anomalies happen everywhere around the world. And these are becoming more frequent, right? Especially the heat waves are becoming more frequent in the ocean. And because this can have a strong impact, for example, what we've seen coral bleaching, primary productivity, reducing primary productivity, mortality of fish species, and so on, depending on the intensity and duration of the.
Marlos, I'm sorry to interrupt you, but the sound of your mic is going up and down, and it's sometimes difficult to hear you well.
Oh, right. Can you hear me better now?
Yeah, now it's better. Yeah.
Yeah, it's better.
Yeah.
Is it still the app or is it still on?
I mean, it sounds better now.
Oh yeah. Okay. If there's a problem, let me know, Matthew. Thank you.
Okay, sorry for interrupting.
Yeah. So for the South Atlantic, a recent paper was by Regina Rodriguez et al. In 2019. They analyzed in the western side of the South Atlantic what would be triggering these events, these warm events, and what the conclusion they came to is that they're most linked to these atmospheric blocking events due to Madden-Julian oscillation. So this oscillation will have a Rossby wave train coming from all the way from the Pacific Ocean, and depending on its phase there when it reaches the western South Atlantic, if it's positive anomaly, it can have a reduction of the cloud cover, so we have a stronger short wave incidence over the ocean, so it warms the ocean, and at the same time it reduces the winds, and so reduce the winds, it also reduces the latent heat flow. So both effects tend to increase the temperature. But the things that blocking events are generally associated to this intraseasonal variability, right? So it's a very intraseasonal phenomenon of this MJO. And the idea here is to try to study what would be modulating these events at longer time scales. Objective here. So to give a little history of what you want to analyze, so in a paper a couple years ago, there was a marine heat wave inciding over the western South Atlantic, a little bit further north, around 22 south, a little further north from the region we want to analyze today. But we see that first we had the cyclonic wind anomalies associated to these events, which is also increased the coastal upwelling here. And by the time we have the arrival of the events, we have strong warm anomalies coming, and then we have a later propagation, this southward. And you see also the effect on the sea level anomalies. We see a strengthening of the sea level anomalies when you have reaching these anomalies and propagating south. So it's all due to this propagation side to, of course, an oceanic mechanism. And by doing here some monthly anomalies, now we have two snapshots of December 2009 when it reached the region, and in February 2010. So we see it's very clear this propagation southward of these events towards more or less the region of our interest, and also the increase in sea surface height. And by using the XBT data, the AX97 in that region, we saw that really although it was warm everywhere else, we have cooling and freshening anomalies from this upwelling of the central waters of the Brazil coast, and also an increase of the Brazil current as well. So yeah, this is a little motivation, and so the objective of this work is to determine the role of these propagating features, and I will focus in one particular feature that I will explain in a little bit, in modulating these marine heat wave events in the West and South Atlantic. And later, okay, thank you, Sanki. And later, I will examine the potential mechanisms of this propagation. So the presentation, the outline, first I'll do the definition of the propagating modes I will be analyzing, which will be done through this method, this complex COF. And we have the calculation, and then the calculation of marine heat waves and cold spells using the metrics defined in this paper, Hobday et al. 2016, that became like the standard for the ocean. And then I'll talk about the mechanism and potential prediction of these propagating features. So to define the propagating features, we will use the definition that was applied in my Junder et al. 2019. So in this paper, we define it with the complex empirical orthogonal functions, COF. So the COF, it gives you the spatial and temporal propagation of these anomalies. And we here analyze that from daily anomalies of sea surface height, then we use the band pass, the interannual time scales. So we see that especially the first mode is pretty clear, this propagation from east to west, and it takes from 2 to 5 years to propagate all the way. And by the time scale similar to the Rossby waves in the ocean. So I have this propagation, so I'll focus first in this first mode here, which is the stronger. And why I'm focusing that? Because if we correlate, so we have here the phase propagation of this mode, the spatial propagation at different phases. So the angle of the phases here on the top, and we see that when you have these anomalies here, negative anomalies of sea surface height, we have a strong negative anomalies of SST. So this is the correlation with SST. So we have at the same time that when negative anomalies of sea surface height arrive, I have negative anomalies of SST. And then by looking at this propagation, so we see the propagation of this now positive anomaly of sea surface height, and we see now the mode turning into now a positive, and this will go back to the initial phase here, but the opposite sign. So we see that as this mode propagates, we have the anomalies of SST propagate. So we see that also there's a propagation not only along this mode propagation, but actually around it. And as it goes around, for example, from south, and then it goes back to north. And I'm going to explain the mechanism. So look at this propagation of this surface height propagation at the interernal time scale. So we see that look at the contours here, the aviso anomalies of surface height anomalies from aviso contour, and the field is the temperature at 300 meters from Oros 5. So we see that that generally these anomalies are associated with the thermostatic component of the sea level. And we see that not only at the surface, but actually sometimes even at the subsurface, we have these anomalies. For example, this one in 2005. And this is the anomalies, temperature anomalies, average in this region between 25 and 32 south, and in two different longitudes. So we see that this anomaly can sometimes even subsurface intensified, not only surface. So, okay, so I'll define what the marine heat waves now. So the marine heat waves we define as the 90th percentile of the daily sea surface temperature anomalies. And so to be a marine heat wave, right, following the ARO 2016, we need at least 5 days from the beginning to the end of the event. And it can have a gap of 2 days, but at least we need 5 days and a gap of 2 days, and then 5 more days to be defined as the same event, otherwise it will be different. And then from these, we can calculate different metrics, such as the maximum intensity, cumulative intensity, duration, and frequency. So this is for the 90 percentiles for marine heat waves, and the cold spell would be the opposite, would be the 10th percentile of these temperature anomalies in each particular grid point. And because we calculate for each grid point, to be able to analyze this in terms of a large-scale process, we do a cluster mode from these temperature anomalies. So we can calculate separately these modes for cold spells and for marine heat waves. So we have we want to focus in this region here, where this region is the one that we have that propagating mode of sea surface height, where the most is the domain where most intense in these regions. So we have here, we define these modes, and we define the daily events of these modes are here as the time series in the bottom. We see that although it's the trended SST, but we still see a little bit of a trend going more towards more cold spells within like the first 10, 15 years, and more marine heat waves more towards the end of the time series. So what we do, we put these two together, these two time series together, and define this as only one mode with the positive and negative phase. And this is what we do. We have this time series now, both together with negative and positive phase of these extreme events. And I plot here on the top in gray what is the reconstruction of the sea surface height using this complex EOF, just one mode of complex EOF, that main mode that propagates from east to west. And we see a really strong relationship between the two. So it seems that at least at the interernal time scales, is driving the modulation of these events. And to calculate how much they are like to be together, so we calculate this what we call conditional probability. So we calculate the probability of the marine heat wave, the cold spell event, happen given that we have a phase of the COF mode. So this is the answer we want. So to estimate these conditional probability events, we have we calculated the Bayes theorem. So the Bayes theorem is actually used is one of the most used methods to calculate events, in which you have the event A here conditional to, for example, the sign of event B is the probability of both events happen at the same time, multiplied by the probability of the first event to happen, divided by the probability of the second event. And in this case here, we have A, right? We have the marine heat waves and cold spells, so it's a binary variable. And B is also a binary variable, it depends on the sign of the COF mode. And if calculated this probability for, so since we have two of each, A and B, right, a positive and negative sign, we can calculate 4 conditional probability. And what you see here is that when you have marine heat waves and the COF plus, the COF is positive, the CSF size is positive, or the cold spells and the CSF size is negative, we have almost 70 and 84% of the case we have together with the events of marine heat waves and cold spells. Whereas if they are out of phase, this probability is much less. So by doing the joint probability of the in-phase relationship between the two, we have 77% of the cases happen when the COF modes in phase with the heat wave.
No.
I think somebody has the phone is open. It's in the background. So if we analyze now in terms of the annual mean of the events for the different metrics that we can calculate for marine heat waves, which is frequency, maximum intensity, and duration here. And we have exactly for, depending on the phase of the complex UF and the CSF side, we have different, we have a very different events for here in blue the cold spells and in red the marine heat waves. So when it's negative, we have very little frequency and intensity and duration of marine heat waves, whereas we have the opposite sign for the cold spells. And if you look at their patterns in a composite analysis for these years that we have, for example, for this in case of a positive COF, these two events here. So we average these two events, and we have exactly the opposite pattern for marine heat waves and cold spells. And it's interesting to see like this dipole of events here. For example, when you have increased the frequency in the western side of the basin for heat waves, we have a decrease on the eastern side of the basin. So we have really clear this dipole mechanism. And the opposite, of course, occurs for the cold spells. So these seem to be exactly the link between these propagating anomalies from east to west and the metrics of marine heat waves. So now we talk about the mechanisms. So what would be the mechanisms doing that? Would be just the oceanic mechanism or atmospheric mechanism as well. So we have here on the left the 3 phases of the COF mode, the propagating mode. We see the propagating mode is positive blob going here to the western side, and the negative starts on the eastern side. So for 3 different phases here, and we also put composites of the QNet, so this is the fluxes into the ocean, and the SST anomalies. So you see that when it's positive here in the middle of the basin, we have also here the SST anomalies positive in this case. And in the eastern side here, in the western side, you have a negative phase of sea surface height, but positive QNet. So QNet tends to warm the ocean, whereas you have cold anomalies. So we tend to increase it. Right? It helps this propagating anomaly to increase the temperatures here, and we see the mechanism here as it propagates. And you have in a second phase where it arrives here, the QNet is not doing too much here, but tends to cool down a little bit. And then you see this anomaly now propagated here to the west. And in this third phase, we have it arrived, the positive anomaly arrived here, sea surface height, and we have a QNet trying to damp this anomaly and damping the sea surface temperature anomaly here. So it seems that the advection brings this anomaly there, and the heat fluxes tend to damp this after and help with this propagating pattern damping process. But also we see that, as I saw at the beginning, now we want to analyze the role of the advection to the heat fluxes. So we see that, so here I use a little spatial filtering just to see better how the advection occurs for this event. So we have, again, the propagation of the mode from east to west. So we have this negative anomaly going towards the west. And here we calculate the geostrophic velocities around this force. And you see that the geostrophic velocity tend to go around these blobs. Right, when it's positive is counterclockwise, and it's negative is clockwise. So I have this circulation around this. And if you look at the temperature anomalies, so you see that the temperature anomalies, they are kind of a little bit displaced from the main core of the sea surface height anomaly. But if you look at this propagation, we see exactly when you have this warm blob here of sea surface height, we have ocean velocities and the advection of more like tropical waters towards the subtropical region, and the opposite for the negative. So for the negative side, we have a northward velocities and advect these cold anomalies towards the region. So we see that in all different phases, and we plot these velocities here on the top of the temperature anomalies, and we see that they are really in phase to each other. So depending on their rotation, it can bring more tropical waters towards the region or more subpolar water towards the region, and this would be the mechanism involved in that. And at the end, so we see that the COF can be a good predictor for the marine heat waves, right? 77%. But what could predict the COF, right? So we have this propagating anomalies from east to west, and several studies, like there's a recent one by Bodnariu, 2021, that they state that this propagating anomaly is not only contained to one basin, but is like a multi-basin process of anomalies, for example, in the Atlantic, coming from the Indian Ocean all the way to the Atlantic. And another paper of 2010 from Dima and Lohman, it has this pattern here, this dipole, as proxy for the AMOC variability and AMOC trend in models. So what we do, we use, there's a reconstruction here, a paper by Shinfu in 2015, where she reconstructed the AMOC in 4 different latitudes in the South Atlantic. And we need to see, we want to see if the AMOC could be linked to these anomalies, could be a predictor for these propagating events. And what we see here is that a really strong correlation of the AMOC, especially in 30 South, a really strong correlation between the loading of this propagating feature and the AMOC. So, and it works for all 4 different latitudes. Not too much on 34 South, but 34, 35 South is a little bit south of the region here of the most of the variability, but there's still some correlation there. But the most of the correlation is on 25 and 30 South, where we have exactly the mode. We have this dipole here in the region. And so what we do, we reconstruct the sea surface height here in the eastern side of the basin, and we see what would be the lag relationship between the sea surface height and the AMOC. And we see that the AMOC actually leads this mode by up to 5 months. It leads this variability here in the eastern side, so it can be a precursor for the development of the anomaly and for the propagation. So what we conclude from this work is that we have that this main propagating mode of sea surface height anomaly is associated to warmer and colder Western South Atlantic, depending on the phase. And this phase is locked with these marine heat waves and cold spells event, that it's 77% of them happen at the right phase of the mode. And this mode, what it does is linked to this advection either from subpolar or tropical waters into the subtropical region. So it do this circulation. It can bring more tropical or tropical warm water or cold subpolar water to the region. And the AMOC can serve as a precursor and mean this for this. So we need to analyze more what is this relationship between the AMOC and the mode. But I think it's pretty clear that the AMOC is leading this propagation feature in the ocean. So thank you. That's all I have